Imagine standing in an empty field on a clear night, gazing up at the stars. For most of human history, this view represented something absolute and unchanging. The stars hung in what Isaac Newton called absolute space, a cosmic stage that existed independently of the actors performing upon it. Time flowed uniformly everywhere, like an invisible river carrying all events at the same steady pace. This was the universe of common sense, where space was simply the container for everything that existed, and time was the universal clock ticking away the seconds. But this comfortable picture began to crack in the early 1900s. A young patent clerk named Albert Einstein was asking uncomfortable questions. What if space and time weren't separate entities? What if they formed a unified fabric that could bend, stretch, and ripple like the surface of a pond? What seemed like philosophical speculation would soon reshape our understanding of reality itself. The revolution began with a simple observation that troubled physicists for decades. Light always travels at the same speed, regardless of how fast you're moving when you measure it. This fact, seemingly innocent, demolished the foundations of classical physics. If light behaves this way, then space and time themselves must be elastic, adjusting themselves to keep light's speed constant. When you move very fast, space contracts and time dilates. What you consider simultaneous, someone moving, relative to you, might see happening at different times. This was Einstein's special theory of relativity, published in 1905. But Einstein wasn't finished. Special relativity worked beautifully for objects moving in straight lines at constant speeds. But what about acceleration? What about gravity? The answer would take him another 10 years to discover, and it would change everything we thought we knew about the cosmos. Picture a person standing in an elevator. If the elevator accelerates upward, they feel pressed against the floor with a force indistinguishable from gravity. Einstein realized this wasn't just an analogy, it was a profound truth. Gravity and acceleration are the same phenomenon viewed from different perspectives. But this insight led to an even more startling conclusion. If gravity feels like acceleration, and acceleration curves the paths that objects follow, then gravity must be the curvature of space-time itself. Imagine space-time as a stretched rubber sheet. A massive object, like the sun, creates a depression in this sheet, much like a bowling ball would create a dip if placed on a trampoline. Smaller objects, like planets, follow curved paths around this depression, not because some mysterious force pulls them, but because they're simply following the straightest possible path through curved space-time. What we call gravity is nothing more than the geometry of the universe itself. This geometric view of gravity became Einstein's general theory of relativity, published in 1915. The mathematics were beautiful, but formidable. Einstein's field equations related the curvature of space-time to the energy and matter within it. In simple terms, matter tells space-time how to curve, and curved space-time tells matter how to move. It was an elegant dance between geometry and physics. The immediate consequences were stunning. General relativity predicted that massive objects would bend light rays, that time would run slower in strong gravitational fields, and that gravitational waves would ripple through space at the speed of light. Each prediction was eventually confirmed by experiment, cementing Einstein's theory as one of the greatest intellectual achievements in human history. But Einstein's equations contained mysteries that even he didn't fully appreciate. They weren't just descriptions of how individual objects moved through space. They were blueprints for entire universes. The equations didn't just tell you how a planet orbits a star, they revealed the possible shapes and fates of all existence. This was both thrilling and terrifying. Mathematics was no longer just a tool for calculating planetary motion, it had become a window into the deepest structure of reality. The first person to peer through this window was Karl Schwarzschild, a German astronomer and physicist. Within months of Einstein publishing his field equations, Schwarzschild found an exact solution describing the spacetime around a perfectly spherical, non-rotating, massive object. Tragically, Schwarzschild died of an autoimmune disease contracted while serving on the Russian front in World War I, just months after his discovery. But his solution revealed something profound. The equations predicted the existence of regions where space-time curvature becomes so extreme that nothing, not even light, can escape. These would later be called black holes. Schwarzschild's solution was just the beginning. Einstein's equations were like a vast landscape waiting to be explored, filled with exotic possibilities that challenged every assumption about the nature of reality. Some solutions described universes that expanded forever, others that collapsed back on themselves. Some contained regions where cause and effect broke down, others where time itself could flow in loops. Yet for all their mathematical beauty, these solutions seem disconnected from the real universe we inhabit. Einstein himself struggled with the cosmological implications of his theory. When he first applied his equations to the universe as a whole, he discovered something unexpected and unwelcome. His equations predicted that the universe could not remain static. It had to be either expanding or contracting. This conclusion troubled Einstein deeply. The universe of 1915 appeared static and eternal. Galaxies beyond the Milky Way hadn't even been discovered yet. The idea of a dynamic, evolving universe seemed not just wrong, but almost absurd. Surely the cosmos was a stable, unchanging entity that had always existed and always would exist. To fix this problem, Einstein made a fateful decision. He modified his elegant field equations by adding a new term, a cosmological constant represented by the Greek letter lambda. This constant acted like a repulsive force that could balance gravity's attraction, allowing the universe to remain static. It was mathematically consistent, but felt like a hack, an artificial addition to preserve a preconceived notion about cosmic stability. The cosmological constant worked, at least on paper. With the right value of lambda, Einstein could construct models of static universes that neither expanded nor contracted. But this solution came at a cost. The modified equations were more complex and less elegant. Worse, they introduced a new mystery. What physical process could create this cosmic repulsion? Einstein's discomfort with the cosmological constant grew over the years. When Edwin Hubble discovered in 1929 that distant galaxies were indeed racing away from us, proving that the universe was expanding just as the original equations predicted, Einstein reportedly called the cosmological constant his greatest blunder. The universe didn't need to be static after all. It was a dynamic, evolving entity born from an initial state of incredible density and temperature. But the story didn't end there. The cosmological constant, once discarded as an embarrassing mistake, would return to haunt cosmology decades later. By the end of the 20th century, astronomers would discover that the universe's expansion is actually accelerating, driven by some mysterious dark energy that behaves remarkably like Einstein's original cosmological constant. The term he regretted most might have been one of his greatest insights. The lesson from this intellectual journey is profound. The universe revealed by Einstein's equations is far stranger and more wonderful than our everyday experience suggests. Space-time isn't just a passive stage where cosmic events unfold. It's a dynamic participant in the cosmic drama. It can bend, ripple, expand, and perhaps even tear. Understanding the universe means understanding the geometry of space-time itself. This geometric revolution opened new questions that continue to challenge physicists today. If space-time can curve and ripple, what determines its overall shape? Are there regions of space-time so exotic that they lie beyond our cosmic horizon? Could there be other universes with different geometric properties, existing alongside our own, but forever hidden from view? The answers to these questions would require exploring solutions to Einstein's equations that pushed the boundaries of mathematical imagination. Among these exotic solutions, few have captured the attention of physicists, quite like the space-time discovered by a Dutch astronomer in 1917. His name was Willem de Sitter, and his universe was stranger than anyone had dared imagine. The year 1915 marked a turning point in human understanding of the cosmos. Albert Einstein, working in Berlin amid the chaos of World War I, put the finishing touches on what would become his masterpiece, the general theory of relativity. The equations he wrote down that November were deceptively simple in appearance, but they contained within them the seeds of a revolution that would reshape our conception of space, time, and the very nature of existence itself. Einstein's field equations can be written in a form that fits comfortably on a t-shirt, yet they encode the fundamental relationship between matter, energy, and the curvature of space-time. On one side of the equal sign sits a mathematical object describing how space-time bends and warps. On the other side sits another object representing the density and flow of matter and energy. The equation simply states that geometry equals physics, that the shape of space-time is determined by what fills it. But extracting the consequences of these equations proved to be a monumental challenge. Unlike the familiar equations of Newton's mechanics, which could be solved with straightforward algebra and calculus, Einstein's field equations were a system of 10 coupled non-linear partial differential equations. They related quantities that varied from point to point throughout space-time, creating a mathematical web of incredible complexity. The non-linear nature of the equations meant that if you found two solutions, their sum wouldn't necessarily be another solution. This made it nearly impossible to build up complex solutions from simpler ones. Each new solution had to be discovered through mathematical ingenuity, physical intuition, or sometimes pure luck. It was like trying to navigate a vast landscape where every step forward revealed entirely new and unexpected terrain. Einstein himself was among the first to grapple with these challenges. He realized that to understand the implications of his theory, he needed to find exact solutions to his field equations for situations of physical interest. The most obvious starting point was to model the universe as a whole, treating it as a single, vast system governed by the laws of general relativity. This cosmological application of general relativity seemed almost audacious. Here was Einstein, barely 40 years old, attempting to describe the entire universe with a set of equations he had just discovered. The scale was unprecedented. Previous physics had dealt with objects ranging from atoms to planets to stars. Now, Einstein was proposing to encompass everything that exists within a single mathematical framework. The challenge was formidable. To apply general relativity to the whole universe, Einstein needed to make assumptions about what the universe looked like on the largest scales. Observations in 1915 were primitive by today's standards. The existence of galaxies beyond our own Milky Way was still unknown. The cosmic microwave background wouldn't be discovered for another 50 years. Einstein had to proceed based on philosophical principles rather than detailed observational evidence. The principle he chose was elegant in its simplicity, the cosmological principle. This stated that on sufficiently large scales, the universe should look the same everywhere and in every direction. There should be no special places or preferred directions in space. Every observer, regardless of their location, should see essentially the same cosmic vista when they look out at the universe on its grandest scales. This assumption of homogeneity and isotropy dramatically simplified Einstein's field equations. Instead of dealing with 10 coupled equations relating quantities that could vary arbitrarily throughout space-time, he now had a much more manageable system. The universe could be described by a single function that determined how its size changed with time, along with equations relating this cosmic scale factor to the matter and energy density within the universe. But when Einstein solved these simplified equations, he encountered a disturbing result. The mathematics predicted that the universe could not remain static. Depending on the amount of matter and energy it contained, the universe had to be either expanding or contracting. There was no middle ground, no stable configuration where cosmic expansion exactly balanced gravitational contraction. This prediction flew in the face of everything that seemed reasonable about the cosmos in 1915. The universe appeared eternal and unchanging. The stars in the night sky occupied the same positions that ancient astronomers had mapped thousands of years earlier. Even the relatively rapid motion of planets followed predictable cycles that repeated endlessly. The idea that the entire fabric of space itself might be expanding or shrinking seemed not just unlikely, but almost nonsensical. Einstein's philosophical commitment to a static universe ran deep. It wasn't simply that observations suggested the universe was static, though they did. More fundamentally, Einstein believed that a truly satisfying cosmological model should describe an eternal, self-consistent universe that had no beginning and would have no end. A dynamic universe raised uncomfortable questions about origins and ultimate fates that seemed to push physics into the realm of metaphysics. Faced with this conflict between mathematical prediction and physical intuition, Einstein made a decision that would haunt him for the rest of his life. He modified his beautiful field equations by adding a single term, a cosmological constant denoted by the Greek letter lambda. This constant represented a new type of energy density that filled all of space, even regions that appeared to be completely empty. The cosmological constant had a remarkable property. Unlike ordinary matter and energy, which created attractive gravitational effects, lambda generated a repulsive force. This cosmic repulsion could exactly balance the attractive pull of gravity, allowing the universe to remain in perfect static equilibrium. With the right choice of lambda, Einstein could construct cosmological models that neither expanded nor contracted, but remained forever unchanged. Mathematically, the modification was elegant. The cosmological constant term fit naturally into the structure of Einstein's equations. It didn't break any symmetries or violate any fundamental principles. From a purely formal standpoint, there was no reason to exclude such a term. The original field equations without lambda were just a special case where the cosmological constant happened to equal zero. But physically, the cosmological constant was deeply mysterious. What could create this uniform energy density that permeated all of space? Unlike ordinary matter, which clumped together to form stars and galaxies, the cosmological constant had to be perfectly smooth and uniform. It couldn't vary from place to place or change with time, otherwise it would disrupt the homogeneity and isotropy that Einstein had assumed. Moreover, the cosmological constant had to have exactly the right value to create a static universe. Too large, and cosmic repulsion would overcome gravity, causing the universe to expand. Too small, and gravity would win, leading to cosmic collapse. The required fine-tuning seemed almost miraculous, like balancing a pencil on its point. Even the tiniest deviation would send the universe flying off in one direction or another. Despite these concerns, Einstein published his cosmological model with the lambda term in 1917. The resulting spacetime, known as the Einstein static universe, described a cosmos that was finite in size but unbounded, like the surface of a sphere extended into 4 dimensions. This universe contained a finite amount of matter, distributed uniformly throughout space, held in perfect equilibrium by the balance between gravitational attraction and cosmological repulsion. The Einstein static universe was mathematically consistent and philosophically appealing, but it came at a cost that Einstein hadn't fully appreciated. The equilibrium was unstable. Like a pencil balanced on its point, the slightest perturbation would cause the universe to start expanding or contracting. If even a tiny bit of extra matter appeared anywhere in the cosmos, or if the cosmological constant fluctuated by the smallest amount, the delicate balance would be broken forever. This instability meant that the Einstein static universe couldn't actually exist in the real world, where quantum fluctuations and other disturbances would inevitably disrupt any perfect equilibrium. But Einstein didn't recognize this problem initially, and neither did most other physicists of the time. The mathematical tools needed to analyze the stability of cosmological solutions wouldn't be developed for several more decades. While Einstein was struggling with the cosmological implications of his theory, other mathematicians and physicists began exploring different solutions to the field equations. They approached the problem from a more purely mathematical perspective, seeking exact solutions without worrying too much about their physical interpretation. This approach would prove remarkably fruitful, revealing exotic possibilities that Einstein himself had never considered. Among these mathematical explorers was Willem de Sitter, a distinguished Dutch astronomer who had become fascinated by Einstein's theory. De Sitter had been corresponding with Einstein about general relativity since its early development, and he had a deep appreciation for both the mathematical elegance of the theory and its potential astronomical applications. But de Sitter approached the cosmological problem from a different angle than Einstein. Instead of insisting that the universe be filled with matter, de Sitter wondered what would happen if space were completely empty. Could general relativity describe a universe that contained nothing but the gravitational field itself? The question seemed almost philosophical, but de Sitter had the mathematical skills to turn it into a rigorous investigation. What de Sitter discovered would challenge every assumption about the relationship between matter, space, and time. His solution described a universe that was completely empty of matter and radiation, yet still possessed a rich and dynamic space-time geometry. This empty universe wasn't static like Einstein's model. Instead, it was expanding exponentially, growing larger at an ever-increasing rate, even though it contained nothing to drive this expansion except the cosmological constant itself. The de Sitter universe seemed to violate common sense. How could empty space expand? What was there to expand? But the mathematics was unambiguous. Einstein's field equations, modified by the cosmological constant, permitted solutions where space-time itself possessed an intrinsic tendency toward expansion that required no material cause. This discovery opened a new chapter in cosmological thinking. The universe described by general relativity was far stranger and more varied than anyone had imagined. Matter and energy weren't just passengers riding through a fixed space-time arena. They were active participants in a cosmic dance where geometry and physics intertwined in ways that defied everyday intuition. De Sitter's empty, exponentially expanding universe would initially be dismissed as a mathematical curiosity, with no relevance to the real cosmos. After all, our universe is obviously filled with matter and radiation. But this seemingly abstract solution would eventually prove to be one of the most important discoveries in theoretical physics. It would provide the key to understanding both the earliest moments of cosmic history and the ultimate fate of everything that exists. The stage was set for a revolution in cosmological thinking that would unfold over the next century. Einstein's equations had revealed that the universe was not the static, eternal entity that philosophers had long imagined. Instead, it was a dynamic, evolving system capable of expansion, contraction, and transformations that pushed the boundaries of human comprehension. The cosmological constant, initially introduced as a reluctant modification to preserve cosmic stasis, would prove to be one of the most prescient additions in the history of physics. In the quiet halls of Leiden Observatory, Willem de Sitter sat surrounded by astronomical charts and mathematical notebooks, pondering a question that would reshape cosmology forever. The year was 1917, and while the world was consumed by the final throes of the Great War, de Sitter was engaged in a different kind of battle. wrestling with the deepest mysteries of space-time itself. De Sitter was no ordinary astronomer. Born in 1872 in the Dutch countryside, he had developed an unusual combination of observational skill and mathematical sophistication that made him uniquely qualified to tackle Einstein's field equations. His early work on the moons of Jupiter had established his reputation as a meticulous observer, but it was his fascination with celestial mechanics and mathematical physics that would prove most consequential. Unlike many of his contemporaries who viewed Einstein's theory with suspicion or bewilderment, de Sitter immediately grasped its revolutionary potential. He had been among the first astronomers outside Germany to fully understand general relativity, and he saw opportunities where others saw only confusion. While Einstein was struggling to force his equations into agreement with a static universe, de Sitter was asking a more fundamental question. What did the equations themselves want to tell us? The inspiration for de Sitter's breakthrough came from an almost philosophical thought experiment. What would happen, he wondered, if we could strip away all the matter and energy from the universe, leaving behind only the bare framework of space-time itself? It seemed like an abstract question with no practical relevance, but de Sitter had learned to trust mathematical exploration, even when it led into seemingly empty territory. This wasn't merely an exercise in mathematical aesthetics. De Sitter understood that by studying extreme cases, physicists often discovered principles that remained hidden in more complicated situations. Just as studying the behavior of an ideal gas revealed fundamental laws that applied to real gases, perhaps studying an ideal empty universe might reveal deep truths about cosmic structure. The mathematical journey began with Einstein's field equations in their modified form, including the cosmological constant. But instead of assuming the universe was filled with matter like Einstein had done, de Sitter set all the matter and energy terms to zero. This left him with a surprisingly simple equation. The curvature of spacetime had to equal the cosmological constant multiplied by the metric that described the geometry of space and time. At first glance, this seemed almost trivial. With no matter present, one might expect space-time to be completely flat, like an empty sheet of paper. But the cosmological constant changed everything. Even in the complete absence of matter, lambda acted like a source of curvature, bending and shaping space-time according to its own mysterious influence. Solving this simplified equation required all of de Sitter's mathematical skill. He needed to find a geometry that was perfectly uniform in space and time, yet possessed the precise amount of curvature demanded by the cosmological constant. The solution, when it finally emerged from his calculations, was breathtaking in its strangeness. De Sitter's universe was a four-dimensional hyperboloid embedded in a five-dimensional flat space. This geometric construction might sound abstract, but it had immediate and startling physical consequences. Unlike Einstein's static cosmos, de Sitter space was inherently dynamic. It expanded exponentially, doubling in size at regular intervals like a cosmic bacterial culture, growing in an infinite petri dish. But here was the truly mind-bending aspect. This exponential expansion occurred in the complete absence of any driving force that classical physics would recognize. There was no matter pushing outward, no energy flowing from dense regions to sparse ones. The expansion emerged purely from the geometry of space-time itself, as if the fabric of reality possessed an innate tendency toward growth. To understand what this meant, de Sitter performed a series of thought experiments. Imagine, he proposed, that we could somehow place test particles at various locations within this empty, expanding space. These particles wouldn't interact with each other or with any material substance, since none existed. They would simply follow the straightest possible paths through the curved geometry of space-time. The results of this Gedanken experiment were revolutionary. Despite following perfectly straight lines in their local space-time, the test particles would appear to accelerate away from each other when viewed from any particular observer's perspective. The expansion of space itself would carry them apart at ever-increasing speeds. creating the illusion of a repulsive force, even though no actual forces were acting. This was the first clear demonstration that expansion could be a property of space itself, rather than a consequence of material processes. In De Sitter's universe, space didn't expand because things within it were pushing outward. Instead, the very concept of distance was evolving, stretching the intervals between any fixed landmarks at an exponentially increasing rate. De Sitter's calculations revealed another surprising feature of his cosmic solution. Unlike Einstein's finite static universe, De Sitter space possessed horizons beyond which communication became impossible. If two observers started far enough apart, the expansion of space would eventually carry them away from each other faster than light could travel between them. They would disappear from each other's observable universe, creating pockets of causally disconnected space-time. These horizons weren't physical barriers like the event horizon of a black hole. Nothing prevented matter or energy from crossing them. Instead, they represented the ultimate limits of information exchange in an exponentially expanding universe. Light signals sent from beyond the horizon would never catch up with the runaway expansion of space itself. The implications were profound and unsettling. De Sitter's universe suggested that space-time could possess a rich and complex structure, even in the complete absence of matter. The classical view of space as a passive container for physical events was clearly inadequate. Space-time was an active participant in cosmic evolution, capable of dramatic transformations that owed nothing to the material contents of the universe. When De Sitter first presented his solution to the scientific community, the reaction was mixed. Some physicists were intrigued by the mathematical elegance of the result, but many others dismissed it as an irrelevant curiosity. After all, our universe is obviously not empty. Stars, planets, gas clouds, and radiation fill space throughout the cosmos. What possible relevance could a completely empty universe have to understanding the real world? This criticism seemed reasonable at the time, but it missed the deeper significance of De Sitter's work. He had discovered a new type of cosmological solution that revealed unexpected possibilities within Einstein's theory. Even if his empty, expanding universe didn't directly describe our cosmos, it might represent an important limiting case or provide insights into cosmic behavior under extreme conditions. De Sitter himself was well aware that his solution was highly idealized, but he argued that studying such pure mathematical cases was essential for building physical intuition about general relativity. Just as Newtonian mechanics was first developed by analyzing idealized systems like point masses and frictionless surfaces, cosmology needed simple, exactly solvable models to guide thinking about more realistic, but mathematically intractable situations. The exponential expansion that characterized De Sitter space also had observational consequences that could potentially be tested. If light from distant sources traveled through such an expanding space-time, its wavelength would be stretched by the cosmic expansion, causing it to appear redder than when it was emitted. This cosmological redshift would provide a direct signature of cosmic expansion that astronomers might eventually detect. De Sitter worked out the quantitative predictions of his model with characteristic precision. In his universe, the redshift of distant objects would increase exponentially with distance, creating a specific mathematical relationship between how far away something was and how much its light had been stretched. This provided a concrete prediction that could distinguish De Sitter expansion from other possible cosmic behaviors. But perhaps the most significant aspect of De Sitter's breakthrough was conceptual rather than observational. He had demonstrated that Einstein's field equations contained possibilities that their creator had never imagined. The cosmos described by general relativity was far richer and stranger than anyone had anticipated. Mathematical exploration was revealing new worlds that challenged every preconception about the nature of space and time. De Sitter's work also highlighted the central role of the cosmological constant in determining cosmic behavior. In Einstein's static universe, lambda served merely to balance gravitational attraction. But in de Sitter space, the cosmological constant became the sole driver of cosmic evolution, powering exponential expansion through its mysterious repulsive influence. This elevated the cosmological constant from a reluctant mathematical convenience to a fundamental feature of space-time itself. Lambda wasn't just a term that could be added to Einstein's equations for technical reasons. It represented a deep property of the vacuum, a cosmic field that filled all of space and influenced the largest scale structure of the universe. The conceptual revolution initiated by de Sitter's work would take decades to fully unfold. His empty, expanding universe seemed like a mathematical abstraction in 1917, but it would eventually provide the key to understanding both the earliest moments of cosmic history and the ultimate fate of everything that exists. The stage was set for discoveries that would transform our picture of the universe and our place within it. To truly understand de Sitter's revolutionary discovery, we must venture into the abstract realm of curved space-time geometry, where familiar notions of distance, angle, and direction take on startling new meanings. The mathematics that describes de Sitter space reads like poetry, written in the language of differential geometry, revealing a cosmos whose structure defies every intuition we've developed from living in apparently flat three-dimensional space. Picture a soap bubble floating in the air, its surface perfectly spherical and uniformly curved. Every point on this two-dimensional surface looks identical to every other point. There are no corners, edges, or special locations that break the beautiful symmetry. Now imagine extending this concept into 4 dimensions, creating a hypersphere that curves through a 5th-dimensional space we cannot directly visualize. This is the mathematical home of de Sitter spacetime. But unlike the static surface of our imaginary bubble, de Sitter space pulses with dynamic energy. The hypersphere expands relentlessly, its radius growing exponentially with time, according to a precise mathematical law. At any given moment, space possesses the geometry of a 3-dimensional sphere, but this sphere inflates at an ever-accelerating pace, carrying everything within it along for the cosmic ride. The technical description involves what mathematicians call a hyperboloid of one sheet, embedded in 5-dimensional Minkowski space. This construction might sound forbiddingly abstract, but it provides the most natural way to understand the symmetries and causal structure of de Sitter spacetime. The embedding reveals that de Sitter space possesses the maximum possible amount of symmetry consistent with Lorentz invariance and cosmic expansion. This high degree of symmetry has profound consequences for how physical processes unfold within de Sitter space. Every observer, regardless of their location, sees exactly the same cosmic environment. There are no preferred directions in space, no special moments in time, and no privileged reference frames. The universe looks identical from every possible vantage point, creating a democracy of cosmic perspectives that Einstein would have found deeply satisfying. But this symmetry comes with a price that distinguishes de Sitter space from the flat Minkowski spacetime of special relativity. In flat space, any observer can in principle communicate with any other observer by sending light signals. Given enough time, information can propagate from any point to any other point in the universe. De Sitter space breaks this fundamental connectivity through the emergence of cosmic horizons. The horizons in de Sitter space arise naturally from the exponential expansion of the cosmic scale factor. Imagine standing at any point in this expanding universe and sending out light signals in all directions. These signals travel at the speed of light through the local space-time geometry, following the straightest possible paths through the curved 4-dimensional manifold. But as they propagate, the expansion of space works against them, stretching the distances they must traverse. For nearby regions, the light signals easily outrun the cosmic expansion, and reach their destinations. But beyond a certain critical distance, the expansion becomes so rapid that light signals can never catch up. They remain forever trapped in a race they cannot win, chasing targets that recede faster than the speed of light. This critical distance defines the De Sitter horizon, a sphere of causally disconnected spacetime that surrounds every observer. The existence of these horizons fundamentally alters the nature of physical causality in De Sitter space. Unlike the global causality of flat spacetime, where every event can potentially influence every other event given sufficient time, De Sitter space fragments into causally isolated patches. Each observer lives within a finite volume of spacetime, beyond which no information can ever penetrate. This causal structure has startling implications for the concept of simultaneity. In special relativity, observers moving relative to each other disagree about which events are simultaneous, but they can always communicate to compare their measurements. In De Sitter space, some observers are so far apart that they can never exchange any information whatsoever. The question of whether distant events are simultaneous becomes not just observer-dependent, but literally meaningless. The metric tensor that describes distances and time intervals in De Sitter space takes several different forms depending on the coordinate system chosen to describe the geometry. Each coordinate system reveals different aspects of the spacetime structure, like viewing a complex sculpture from different angles. The choice of coordinates doesn't change the underlying geometry, but it can dramatically affect how that geometry appears to human intuition. In the so-called global coordinates, De Sitter space appears as a hyperboloid with a single time-like coordinate covering the entire spacetime manifold. This description emphasizes the global symmetry and reveals the complete causal structure, but it obscures the local physics that any individual observer would experience. The coordinates become singular at the horizons, making it difficult to understand what happens there. Static coordinates provide a different perspective that closely resembles the familiar coordinate systems used to describe black holes. In this coordinate system, space appears static near any given observer, with the cosmic expansion manifesting as a coordinate singularity at the horizon. This description makes it easy to understand local physics, but hides the global structure of the spacetime. Perhaps most revealing are the flat coordinates, which cover only a portion of the full De Sitter manifold, but describe that portion in terms that closely resemble ordinary flat space with a time-dependent scale factor. In these coordinates, the exponential expansion appears explicitly as a cosmic scale factor that grows exponentially with cosmic time. This is the coordinate system that most closely matches our intuitive picture of an expanding universe. The curvature of De Sitter space manifests in subtle but measurable ways that distinguish it from flat spacetime. Parallel lines that start out running in the same direction gradually converge as the expansion of space curves their paths. The sum of angles in a triangle exceeds 180 degrees, just as it does for triangles drawn on the surface of a sphere. Clocks at different locations in the gravitational field run at slightly different rates, even in the absence of any matter. These geometric effects become more pronounced as we consider larger and larger regions of De Sitter space. Over cosmic distances, the curvature becomes so significant that it fundamentally alters the behavior of light rays, particle trajectories, and even the vacuum fluctuations of quantum fields. The universe reveals its curved nature through subtle deviations from the behavior we would expect in flat space. One of the most remarkable features of De Sitter geometry is its thermal properties. Despite being completely empty of matter and radiation, De Sitter space behaves as if it possesses a finite temperature when viewed from the perspective of any accelerated observer. This temperature arises purely from the geometry of spacetime itself, without requiring any conventional sources of heat or thermal energy. The mechanism behind this geometric thermodynamics involves the quantum mechanical properties of the vacuum in curved spacetime. The accelerated expansion of de Sitter space constantly stretches quantum fluctuations, amplifying virtual particle pairs into real particles that carry energy and entropy. From the perspective of any observer, the vacuum appears to be filled with thermal radiation at a temperature proportional to the cosmic expansion rate. This thermal behavior connects de Sitter space to the deeper mysteries of quantum gravity and black hole thermodynamics. The horizons that surround every observer in de Sitter space share many properties with black hole event horizons, including the ability to hide information and generate thermal radiation. This suggests that the geometric thermal effects in de Sitter space might provide clues about the fundamental nature of space-time itself. The symmetries of de Sitter space also constrain the types of matter and energy that can exist within it. Any matter field that respects the maximal symmetry of the background geometry must be perfectly uniform and isotropic. This rules out localized objects like stars, planets, or galaxies, which would break the cosmic symmetry by creating preferred locations in space. This constraint might seem to make de Sitter space irrelevant to realistic cosmology, since our universe is obviously filled with highly inhomogeneous matter distributions. But the geometric insights provided by the pure de Sitter solution prove invaluable for understanding more complex cosmological models, where small amounts of matter are added to an approximately de Sitter background. The mathematical tools developed to analyze de Sitter geometry have found applications throughout theoretical physics, from particle physics to string theory to quantum field theory in curved space-time. The highly symmetric structure makes de Sitter space an ideal laboratory for testing new ideas about quantum gravity, holography, and the fundamental nature of space and time. Perhaps most importantly, the geometry of de Sitter space provides a concrete realization of cosmic inflation, the hypothetical period of exponential expansion that may have occurred during the earliest moments of our universe's history. By understanding how quantum fields behave in de Sitter spacetime, physicists can make detailed predictions about the signatures that primordial inflation would have left in the cosmic microwave background and the large-scale structure of the universe. The elegant mathematical structure of de Sitter space thus serves as both a theoretical laboratory and a potential description of physical reality. Its geometry encodes profound truths about the relationship between matter, energy, and space-time that continue to guide cosmological research more than a century after de Sitter's original discovery. The most striking feature of de Sitter spacetime emerges when we follow the trajectories of test particles as they move through the exponentially expanding cosmic geometry. Unlike the orderly, predictable motions that characterize planetary orbits or stellar dynamics, particles in de Sitter space experience a form of motion that seems to violate every intuition about cause and effect. They accelerate away from each other despite the complete absence of any physical forces, creating a cosmic choreography driven purely by the evolving geometry of spacetime itself. To understand this phenomenon, imagine placing a collection of dust particles throughout de Sitter space at some initial moment. These particles have no internal structure, no electromagnetic charges, and no ability to interact with each other through any of the fundamental forces. They are simply mathematical points that follow geodesics, the straightest possible paths through the curved four-dimensional manifold of space-time. Initially, the particles might appear to be at rest relative to each other, scattered throughout space in some arbitrary configuration. But as cosmic time advances, something remarkable happens. The particles begin to separate, slowly at first, then with increasing speed. The distances between them grow exponentially, doubling at regular intervals like a cosmic population explosion, driven by the expansion of space itself. This behavior seems to contradict the principle of inertia, which tells us that objects in motion should continue moving in straight lines unless acted upon by external forces. But the resolution lies in understanding what constitutes a straight line in curved spacetime. The particles are indeed following perfectly straight geodesic paths through the de Sitter geometry. It's the geometry itself that's evolving, stretching the meaning of distance and transforming straight-line motion into apparent acceleration. The mathematical description of this process involves the cosmic scale factor, a function that determines how the size of space changes with time. In de Sitter spacetime, this scale factor grows exponentially according to a precise mathematical law involving the cosmological constant. The larger the value of lambda, the faster the exponential growth and the more dramatic the cosmic acceleration. This exponential scaling has profound implications for how we measure distances in an expanding universe. Consider two particles that are initially separated by some fixed physical distance. As time progresses, this distance grows exponentially. But there are different ways to define what we mean by distance in an expanding space-time. The physical distance, measured by the time it takes light to travel between the particles, grows with the cosmic expansion. But the co-moving distance, which factors out the expansion, remains constant. The distinction between physical and co-moving distances becomes crucial when we consider how light propagates through de Sitter space. A photon emitted by one particle and detected by another experiences the full effects of cosmic expansion during its journey. The expansion stretches the wavelength of the light, shifting it toward longer, redder wavelengths in a process that becomes the observational signature of cosmic expansion. This cosmological redshift provides a direct window into the dynamics of space-time expansion. The amount of redshift depends on how much the universe has expanded during the light travel time between emission and detection. In pure de Sitter space, this leads to a specific mathematical relationship between redshift and distance that can be calculated exactly from the geometry of the spacetime. The redshift formula for de Sitter space reveals a startling prediction. For sufficiently distant sources, the redshift becomes infinite, indicating that light emitted beyond a certain distance can never reach any given observer. This marks the location of the cosmic horizon, beyond which communication becomes impossible due to the runaway expansion of space. But the observational consequences of de Sitter expansion extend far beyond simple redshift measurements. The exponential growth of distances fundamentally alters how we perceive the cosmic environment. Nearby objects appear to move away slowly, while more distant objects recede at ever-increasing speeds. The most distant visible objects rush away at velocities that approach, but never quite reach the speed of light. This velocity-distance relationship creates a cosmic velocity field that appears to violate special relativity's prohibition against faster-than-light motion. But the resolution lies in understanding that we're not dealing with motion through space, but rather with the expansion of space itself. The recession velocities we observe are not due to particles actually moving through space-time, but to the stretching of space-time between us and the distant objects. The apparent motion also depends critically on the reference frame used to describe the expansion. In the co-moving frame, which expands along with the cosmic scale factor, the test particles remain at rest throughout the expansion process. The distances between them, measured in co-moving coordinates, never change. It's only when we use physical coordinates that the dramatic recession becomes apparent. This frame dependence highlights a subtle but important point about the nature of cosmic expansion. The expansion is not something that happens to objects within space, but rather something that happens to space itself. Objects that are at rest in the co-moving frame participate passively in the cosmic expansion without experiencing any forces or accelerations in their local reference frames. The energy considerations in de Sitter expansion reveal another counterintuitive aspect of the phenomenon. As space expands and objects move apart, we might expect the total energy of the system to change. After all, If objects are accelerating away from each other, shouldn't this represent an increase in kinetic energy? But in general relativity, energy conservation becomes subtle in curved space-time, especially when the geometry itself is time-dependent. In de Sitter space, the resolution involves understanding that the cosmological constant acts as a reservoir of negative pressure that drives the expansion. As space expands, the cosmological constant does negative work on the cosmic expansion, providing the energy needed to accelerate the recession of distant objects. The total energy, properly defined to include both matter and gravitational contributions, remains conserved throughout the expansion process. This mechanism differs fundamentally from ordinary material expansion, where objects fly apart because they were given initial velocities by some explosive event. In de Sitter expansion, the acceleration is ongoing and self-sustaining. The cosmological constant continuously drives the expansion, creating new space and accelerating the recession of distant objects without any need for an initial explosion or energy input. The self-sustaining nature of de Sitter expansion has important implications for the arrow of time in cosmology. Unlike mechanical systems that tend toward equilibrium as energy dissipates, de Sitter space maintains its exponential expansion indefinitely. There is no cosmic friction or energy loss that would eventually slow the expansion. The universe becomes a perpetual motion machine, powered by the mysterious energy density of the vacuum itself. This timeless quality of de Sitter expansion connects to deep questions about the nature of cosmic evolution. If the expansion never slows down or speeds up, how do we define a cosmic age or measure the progress of cosmic history? The exponential expansion creates a kind of temporal symmetry, where the relative rate of change remains constant, even as absolute scales grow without bound. The answer lies in understanding that while the expansion rate remains constant in de Sitter space, the physical scales continue to evolve. A galaxy that appears nearby today will eventually disappear beyond the cosmic horizon as the expansion carries it away. The observable universe shrinks in co-moving coordinates even as it grows in physical size, creating a dynamic balance between cosmic growth and cosmic isolation. These considerations reveal why de Sitter space, despite its apparent simplicity, captures essential features of cosmic expansion that appear in more realistic cosmological models. The exponential scaling, the horizon structure, the redshift-distance relationship, and the energy dynamics all provide templates for understanding how expansion works in universes that contain matter and radiation, as well as a cosmological constant. The mathematical framework developed to analyze de Sitter expansion has proven invaluable for interpreting astronomical observations of cosmic expansion in our own universe. When Edwin Hubble discovered the linear relationship between recession velocity and distance for nearby galaxies, he was seeing the local approximation to a more general expansion law that, in its pure form, corresponds exactly to de Sitter's mathematical prediction. The connection between de Sitter geometry and observational cosmology became even more direct with the discovery that our universe's expansion is actually accelerating. This acceleration suggests that our cosmos is evolving toward a state that closely resembles pure de Sitter space, where the cosmological constant dominates over matter and radiation and drives exponential expansion into the far future. Understanding de Sitter expansion thus provides the key to interpreting some of the most important discoveries in modern cosmology. From the cosmic microwave background to Type Ia supernovae to gravitational wave observations, many different astronomical phenomena can be understood only by recognizing the fundamental role that space-time expansion plays in shaping the cosmic environment we observe. The story of how de Sitter space transformed from mathematical curiosity to cosmic reality begins in the late 1970s, when a young particle physicist named Alan Guth was struggling with one of the most perplexing problems in cosmology. The universe appeared too perfect, too finely tuned, too uniform to have emerged from the chaotic conditions that standard Big Bang theory predicted for the earliest moments of cosmic history. Consider the cosmic microwave background, the afterglow of the Big Bang that fills all of space with nearly uniform radiation. This radiation exhibits a temperature that varies by less than 1 part in 100,000 across the entire sky. Such extraordinary uniformity seemed to require that widely separated regions of the early universe had somehow communicated and reached thermal equilibrium. But according to standard cosmology, these regions had never been in causal contact. They lay beyond each other's light horizons throughout the entire history of the universe. This horizon problem represented a fundamental challenge to our understanding of cosmic origins. How could regions that had never exchanged information possibly coordinate their properties so precisely? The puzzle deepened when astronomers realized that the universe's geometry appeared to be almost perfectly flat, balanced on a knife edge between eternal expansion and eventual collapse. This flatness problem required initial conditions tuned to extraordinary precision, far beyond what seemed reasonable to expect from random cosmic evolution. Guth's breakthrough came when he realized that these problems could be solved by a brief period of exponential expansion during the universe's infancy. If the cosmos had undergone a phase of de Sitter-like inflation, expanding by enormous factors in tiny fractions of a second, then regions that appear causally disconnected today could have been in close contact before inflation began. The horizon problem would dissolve because the apparently uniform regions had indeed communicated in the pre-inflation era. The mathematical framework for cosmic inflation borrowed heavily from de Sitter's original work, but with a crucial modification. Instead of assuming that the cosmological constant was truly constant, Guth proposed that the early universe was dominated by a scalar field whose energy density mimicked the effects of a large cosmological constant. This inflaton field drove exponential expansion just like lambda does in pure de Sitter space, but unlike the cosmological constant, the inflaton field could evolve and eventually decay. The physics of the inflaton field combined quantum mechanics with general relativity in unprecedented ways. The field existed in a metastable state with enormous energy density, creating the positive pressure needed to drive exponential expansion. But quantum fluctuations caused the field to slowly roll toward lower energy states, like a ball rolling down a very flat hill. When the field finally reached the bottom of its energy landscape, inflation ended and the universe transitioned to the familiar radiation-dominated expansion of the standard Big Bang model. This transition from inflation to standard expansion, known as reheating, represented one of the most dramatic phase changes in cosmic history. The enormous energy stored in the inflaton field was converted into the hot plasma of elementary particles that filled the early universe. In a sense, the Big Bang was not the beginning of the universe, but rather the end of inflation. The moment when the exponential expansion phase gave way to the decelerating expansion driven by ordinary matter and radiation. The duration and magnitude of cosmic inflation were staggering beyond comprehension. Conservative estimates suggest that inflation lasted for at least 60 E-foldings, meaning that the universe expanded by a factor of at least 10 to the power of 26 during this brief epoch. Some models allow for much longer periods of inflation, with expansion factors that dwarf even the largest numbers in ordinary mathematics. To appreciate these scales, consider that a region the size of a proton could have inflated to become larger than a grapefruit during the inflationary epoch. The entire observable universe today, with its 100 billion galaxies spread across nearly 100 billion light-years, might have originated from a quantum fluctuation in a patch of space-time smaller than an atomic nucleus. This enormous expansion had profound consequences for the causal structure of the early universe. Regions that were in thermal contact before inflation began were stretched so far apart that they lost all communication for the remainder of cosmic history. Conversely, Our entire observable universe originated from a causally connected patch that was incredibly tiny before inflation began. This resolved the horizon problem by ensuring that the regions we observe had indeed been in thermal equilibrium at some point in the past. The flatness problem found an equally elegant solution. Inflation acts like a cosmic iron, smoothing out any initial curvature and driving the universe toward perfect geometric flatness. Just as inflating a balloon makes its surface appear flatter and flatter to an ant crawling on it, cosmic inflation stretched any initial curvature to scales far larger than our observable horizon. From our perspective, the universe appears flat because we can see only a tiny patch of what may be a highly curved cosmic manifold. But perhaps the most remarkable aspect of cosmic inflation was its ability to generate the seeds of cosmic structure from quantum mechanical fluctuations in the inflaton field. During the inflationary epoch, quantum uncertainty created tiny variations in the energy density of the inflaton field. These fluctuations were initially microscopic, but the exponential expansion of space amplified them to macroscopic scales while preserving their quantum statistical properties. When inflation ended and the universe entered the radiation-dominated era, these quantum-derived density fluctuations became the seeds around which galaxies, galaxy clusters, and larger cosmic structures would eventually form. The cosmic web of filaments and voids that characterizes the large-scale structure of today's universe can be traced back to quantum fluctuations that occurred during inflation when the universe was less than 1 second old. This connection between quantum mechanics and cosmic structure represents one of the most profound insights in modern physics. The irregularities we observe in the cosmic microwave background, the clustering of galaxies, and even the existence of stars and planets all owe their origins to quantum fluctuations that were frozen into the fabric of space-time during the inflationary epoch. The quantum fluctuations generated during inflation exhibit specific statistical properties that can be calculated using quantum field theory in de Sitter space. These calculations predict that the fluctuations should be nearly scale invariant, meaning that they have similar amplitudes on all length scales. They should also be Gaussian distributed, following the bell curve statistics characteristic of quantum mechanical processes. These theoretical predictions have been tested with extraordinary precision using observations of the cosmic microwave background. The patterns of temperature variations in this ancient radiation provide a direct snapshot of the density fluctuations that existed when the universe became transparent to light, about 380,000 years after the Big Bang. The observed patterns match the predictions of inflation with remarkable accuracy, providing strong evidence that our universe did indeed undergo an inflationary phase. The success of inflationary cosmology in explaining observed features of the universe has made it the standard paradigm for understanding cosmic origins. But this success comes with a price. It requires that the early universe was dominated by physics that extends far beyond the standard model of particle physics. The inflaton field has no known counterpart among the elementary particles and forces that have been directly observed in laboratory experiments. This gap between theory and observation has motivated decades of research into the particle physics of inflation. Theoretical physicists have proposed dozens of different models for the inflaton field, ranging from simple scalar fields with polynomial potentials to complex constructions involving extra dimensions, string theory, and exotic quantum field theory phenomena. Despite this theoretical diversity, nearly all successful inflation models share a common mathematical structure inherited from de Sitter's original work. They require a period when the universe was dominated by something that acted like a cosmological constant, driving exponential expansion through its negative pressure. The specific details of how this de Sitter-like phase began and ended depend on the underlying particle physics, but the geometric and dynamical features of the expansion are largely universal. This universality explains why inflation has proven so robust as a cosmological paradigm. Even as particle physics models come and go, the basic framework of exponential expansion in the early universe continues to provide successful explanations for observed cosmic properties. De Sitter space has evolved from a mathematical curiosity to the foundation of our best theory for cosmic origins. The inflationary paradigm has also opened new frontiers in cosmological research. If inflation occurred once in cosmic history, it might be occurring elsewhere in the universe even now, creating pocket universes with different physical properties. This eternal inflation scenario suggests that our observable universe is just one bubble in an infinite cosmic foam, each bubble representing a different realization of the fundamental laws of physics. The mathematical machinery developed to study inflation has revealed subtle but profound connections between quantum mechanics and gravity that continue to challenge our understanding of fundamental physics. During inflation, the rapid expansion of space-time creates particle pairs from quantum vacuum fluctuations, similar to the Hawking radiation produced near black hole horizons. These particles carry away energy and entropy, suggesting that inflation itself might be subject to thermodynamic laws analogous to those governing black holes. The observational program to test inflation has evolved into one of the most sophisticated efforts in modern astronomy. Future space missions will map the polarization patterns in the cosmic microwave background with unprecedented precision, searching for the distinctive spiral patterns that gravitational waves from inflation would have imprinted on the ancient light. These primordial gravitational waves represent ripples in space-time itself, generated by quantum fluctuations in the gravitational field during the inflationary epoch. The detection of primordial gravitational waves would provide direct evidence that inflation occurred and would open a new window into physics at energy scales far beyond what can be probed in particle accelerators. The amplitude of these waves encodes information about the energy scale of inflation, potentially revealing details about grand unified theories, extra dimensions, or other exotic physics that governed the universe when it was less than a trillionth of a trillionth of a trillionth of a second old. But inflation also raises deep questions about the nature of cosmic beginnings that continue to perplex physicists and philosophers. If inflation can occur once, what prevents it from occurring again? Some models suggest that inflation is eternal into the future, continuously creating new regions of exponentially expanding spacetime embedded within our cosmic horizon. This eternal inflation scenario implies that the observable universe we inhabit represents just one transient episode in an endless process of cosmic reproduction. The implications of eternal inflation challenge traditional notions of cosmic uniqueness and cosmic purpose. If inflation creates infinitely many pocket universes with different physical properties, then our universe loses its special status as the unique arena for physical law. Instead, it becomes just one random sample from an infinite ensemble of possible worlds, selected not by fundamental principles, but by the anthropic requirement that physical conditions must allow for the emergence of observers. This anthropic reasoning has proven both powerful and controversial in contemporary cosmology. It provides a natural explanation for why our universe appears fine-tuned for the existence of complexity and life. In an infinite multiverse, even improbable configurations must occur somewhere, and we necessarily find ourselves in one of the rare universes where conditions permit our existence. But critics argue that anthropic explanations abandon the traditional scientific goal of predicting unique outcomes from fundamental principles. The debate over anthropic reasoning in cosmology reflects deeper questions about the relationship between physical law and cosmic structure that inflation has brought into sharp focus. Does the universe embody mathematical necessity, unfolding according to unique principles that determine its structure completely? Or does cosmic evolution involve elements of chance and selection that introduce fundamental randomness into the deepest levels of physical reality? These philosophical challenges aside, the practical success of inflationary cosmology has established de Sitter space as a central organizing principle for understanding cosmic evolution. The exponential expansion that de Sitter discovered in his abstract mathematical investigation has become the key to explaining both the homogeneity of the early universe and the seeds of cosmic structure that grew into the galaxies we observe today. Mathematics has once again proven its unreasonable effectiveness in revealing the hidden principles that govern physical reality. On a clear night in Chile's Atacama Desert in 1998, astronomers peering through powerful telescopes made a discovery that would fundamentally reshape our understanding of cosmic destiny. They were studying Type Ia supernovae, stellar explosions so brilliant that they can be seen across billions of light-years of space. These cosmic lighthouses serve as standard candles for measuring vast distances because each explosion releases roughly the same amount of energy, allowing astronomers to determine how far away they are by measuring how bright they appear. The Supernova Cosmology Project and the High Z Supernova Search Team were engaged in a cosmic archaeology project using these distant supernovae to trace the expansion history of the universe. Everyone expected the measurements to show that cosmic expansion was slowing down, gradually decelerating under the gravitational pull of all the matter scattered throughout space. The only question was whether this deceleration was strong enough to eventually halt the expansion and cause the universe to collapse back on itself. But the data told a radically different story. The distant supernovae appeared dimmer than expected, indicating they were farther away than predicted by models of decelerating expansion. Instead of slowing down, the expansion of the universe was speeding up. Cosmic expansion was accelerating, driven by some mysterious influence that acted like a repulsive force on the largest scales. This discovery came as a complete shock to the astronomical community. Nothing in the standard model of cosmology had prepared scientists for the possibility that expansion could accelerate. The gravitational effects of ordinary matter and radiation could only slow expansion down, never speed it up. Something else was at work, something that comprised the majority of the universe's energy budget, but had remained completely hidden until these precise supernova measurements revealed its presence. The mysterious component responsible for cosmic acceleration was dubbed dark energy, acknowledging both its invisibility to direct detection and our profound ignorance about its fundamental nature. Dark energy exhibits properties that seem to violate every intuition about how matter and energy behave. Unlike ordinary substances, which become less dense as space expands and their constituent particles spread out, dark energy maintains a constant density even as the universe grows larger. This constant density property means that as the universe expands, the total amount of dark energy increases proportionally to the volume of space. More space means more dark energy, creating a feedback loop that drives ever faster expansion. The universe becomes an exponential growth machine powered by the mysterious properties of the quantum vacuum itself. The simplest and most natural explanation for dark energy involves Einstein's cosmological constant, the same lambda term that he had introduced in 1917 to create a static universe and later called his greatest blunder. A cosmological constant produces exactly the kind of repulsive gravitational effect needed to explain the observed acceleration. It maintains constant density as space expands, and it generates the negative pressure required to drive exponential expansion, according to Einstein's field equations. If dark energy truly represents a cosmological constant, then our universe is evolving toward a future that looks remarkably similar to the de Sitter spacetime that Willem de Sitter discovered over a century ago. As dark energy comes to dominate over matter and radiation, cosmic expansion will approach the exponential behavior characteristic of pure de Sitter space. the universe will enter a phase of eternal inflation that continues indefinitely into the future. Current observations suggest that dark energy already comprises about 70% of the universe's total energy density. Matter, both ordinary and dark, accounts for only about 30%. As expansion continues, the density of matter will continue to decrease, while dark energy density remains constant. Eventually, dark energy will dominate so completely that the universe will become virtually indistinguishable from pure de Sitter space. This de Sitter future has profound implications for the long-term evolution of cosmic structure. As expansion accelerates, the observable universe will paradoxically shrink in comoving coordinates. Distant galaxies will disappear beyond our cosmic horizon as the expansion carries them away faster than light can travel between us. The night sky will gradually become darker and more empty as fewer and fewer galaxies remain visible from any given location. The process begins slowly, but accelerates relentlessly. Galaxies currently at the edge of our observable universe will be the first to vanish, disappearing as their light can no longer overcome the expansion of space. Progressively closer galaxies will follow, creating an ever-shrinking sphere of visibility centered on our local galactic neighborhood. Eventually, even galaxies in our own local group will begin to fade from view as cosmic acceleration overcomes their gravitational binding. This cosmic isolation has dramatic consequences for future astronomy and astrophysics. Civilizations that emerge billions of years from now will inhabit a universe that appears almost empty, containing only the gravitationally bound structures within their immediate cosmic neighborhood. The cosmic microwave background will have been redshifted beyond detection, erasing the observational evidence for the Big Bang. Future astronomers will have no way to deduce the existence of the larger cosmos beyond their shrinking horizon. The expansion will also affect the internal structure of gravitationally bound systems, though much more gradually. Galaxy clusters will eventually be torn apart as the accelerating expansion overcomes the gravitational forces that hold them together. Individual galaxies will follow, losing their outer regions to the cosmic flow. Even solar systems may eventually succumb, though this process would take vastly longer than the current age of the universe. Star formation will gradually cease as the universe expands and cools, exhausting the supply of gas needed to create new stars. Existing stars will burn through their nuclear fuel and fade, leaving behind white dwarfs, neutron stars, and black holes as the only surviving remnants of stellar evolution. The universe will enter a long, cold era dominated by these stellar corpses slowly cooling in the exponentially expanding void. Black holes will provide the final source of energy in this dark future, slowly evaporating through Hawking radiation over timescales that dwarf even geological epochs. A black hole with the mass of the Sun would take longer than 10 to the power of 67 years to evaporate completely, far longer than the universe has existed. But even these processes will eventually run their course, leaving behind only elementary particles scattered through an ever-expanding space-time. The ultimate fate predicted by de Sitter cosmology is a state of maximum entropy where all useful energy has been dissipated and no further organization or complexity can emerge. This heat death scenario represents the logical endpoint of the second law of thermodynamics applied to cosmology. The universe evolves toward a state of perfect thermal equilibrium, where nothing interesting can ever happen again. But this grim prognosis assumes that dark energy truly behaves like a cosmological constant, maintaining constant density throughout future cosmic evolution. Alternative models of dark energy allow for more complex behaviors that could dramatically alter the cosmic forecast. If dark energy density increases with time, the universe might end in a big rip, where acceleration becomes so extreme that it tears apart all bound structures, including atoms themselves. Conversely, if dark energy weakens over time, the universe might return to a phase of decelerating expansion or even eventual contraction. Some models propose that dark energy oscillates, driving cycles of acceleration and deceleration that could repeat indefinitely. Others suggest that dark energy represents a temporary phase in cosmic evolution that will eventually give way to new physics operating on scales we cannot yet comprehend. The quantum mechanical properties of de Sitter space add another layer of complexity to these cosmic scenarios. The exponential expansion creates a thermal environment characterized by Hawking radiation, analogous to that produced by black holes. This de Sitter temperature is incredibly low by everyday standards, but it represents a fundamental limit to how cold the universe can become during the accelerating expansion phase. The thermal properties of de Sitter space also raise profound questions about the nature of information and entropy in cosmology. If cosmic horizons hide information from view and thermal radiation carries entropy away from any given observer, what happens to the total information content of the universe during eternal expansion? These questions connect dark energy to some of the deepest puzzles in theoretical physics. Efforts to understand dark energy have motivated increasingly sophisticated observational programs designed to measure the expansion history of the universe with unprecedented precision. Future space missions will map the positions and redshifts of billions of galaxies, trace the growth of cosmic structure over billions of years, and search for subtle signatures of dark energy's gravitational effects on light propagation through the cosmos. These observations aim to determine whether dark energy truly behaves like a cosmological constant, or exhibits more complex dynamics that could signal new physics beyond general relativity. The answer will determine whether de Sitter space represents our ultimate cosmic destination or merely a temporary phase in a more complex cosmic evolution. The philosophical implications of living in a universe dominated by dark energy extend far beyond technical cosmology. If the de Sitter future is indeed our destiny, then consciousness and intelligence emerge as transient phenomena in cosmic history, flickering briefly during the narrow window when stars shine and planets provide suitable environments for complexity. The vast majority of future cosmic time will be devoid of observers, information processing, or any form of organized activity. This perspective challenges traditional notions of cosmic purpose and meaning, suggesting that the universe we observe represents a rare and temporary oasis of complexity in an otherwise barren cosmic landscape. Yet it also highlights the extraordinary improbability and preciousness of the current cosmic era, when matter has organized itself into the intricate structures that make life and consciousness possible. The transition from matter-dominated to dark energy-dominated expansion represents one of the most significant phase changes in cosmic history, comparable in importance to the transitions from inflation to radiation domination or from radiation to matter domination. Each of these transitions fundamentally altered the character of cosmic evolution, changing which physical processes dominated the dynamics of space-time and matter. During the matter-dominated era, gravitational instabilities could grow and amplify, allowing small density fluctuations to collapse into the hierarchical structures we observe today. Dark matter halos formed first, providing the gravitational scaffolding around which ordinary matter could condense into stars and galaxies. This era of structure formation was characterized by gravitational dynamics that overcame the background expansion to create bound systems of ever-increasing complexity. But as dark energy comes to dominate, this structure formation process gradually shuts down. The accelerating expansion makes it increasingly difficult for gravitational instabilities to grow, preventing the formation of new bound structures on large scales. The cosmic web of filaments and voids that characterizes today's universe represents the final expression of gravitational structure formation before dark energy dominance brings this creative epoch to an end. The detailed timeline of this transition depends sensitively on the precise properties of dark energy and its evolution with cosmic time. If dark energy behaves exactly like a cosmological constant, the transition occurs gradually over many billions of years. Galaxy formation continues for several billion more years, though at a steadily decreasing rate. Star formation persists even longer, sustained by the gravitational collapse of gas within already formed galaxies. But eventually, even these local processes succumb to the global influence of dark energy. The local group of galaxies, which includes the Milky Way and Andromeda, will merge into a single giant elliptical galaxy over the next few billion years. This merged system will remain gravitationally bound despite the cosmic acceleration, creating an island of complexity in an increasingly empty universe. Beyond the local group, other galaxy clusters will follow similar evolutionary paths, merging internally while becoming increasingly isolated from their neighbors. The cosmic web will fragment into disconnected pieces, each evolving independently as cosmic expansion carries them beyond each other's gravitational influence. The universe will develop a cellular structure, with dense nodes of matter separated by vast regions of empty, exponentially expanding space. Within these isolated cells, astrophysical processes will continue for vastly longer periods than the current age of the universe. Low-mass stars will burn for trillions of years, far longer than the 14 billion years that have elapsed since the Big Bang. Brown dwarfs and planetary systems will persist even longer, slowly cooling through thermal radiation while orbiting the stellar remnants left behind by more massive stars. The ultimate energy source in this far future cosmos will be gravitational binding energy, released through stellar collisions and tidal interactions. As stellar orbits decay through gravitational wave emission, binary systems will spiral together and merge, releasing enormous amounts of energy in brief, brilliant flashes. These merger events will provide temporary illumination in an otherwise darkening universe. Stellar evolution will also proceed along new pathways as the universe cools and expands. The cosmic microwave background temperature will continue to drop, eventually falling below the surface temperatures of the coolest stars. At this point, stars will begin to absorb energy from their surroundings rather than radiating it away, potentially extending their lifetimes by enormous factors. The thermodynamics of this far future universe become increasingly exotic as temperatures approach absolute zero. Quantum mechanical effects that are normally negligible will become dominant, leading to phenomena like superfluidity and superconductivity on astronomical scales. Matter may organize itself into crystalline structures spanning entire planets or star systems. Black holes will play an increasingly important role as other energy sources are exhausted. Stellar mass black holes will grow through accretion of surrounding matter, eventually consuming most of the baryonic matter in their vicinity. Supermassive black holes at galactic centers will dominate the dynamics of their host galaxies, slowly accreting matter while emitting jets and radiation that affect their cosmic neighborhoods. But even black holes are not eternal in a de Sitter universe. Hawking radiation causes them to evaporate slowly, with evaporation times that scale as the cube of their mass. Stellar mass black holes will persist for times measured in 10 to the power of 67 years, while supermassive black holes could survive for 10 to the power of 100 years or longer. These timescales dwarf the current age of the universe by factors that challenge human comprehension. The evaporation of black holes represents the final phase transition in cosmic evolution, marking the end of the last sources of organized energy in the universe. As the final black holes disappear in flashes of Hawking radiation, the cosmos will enter its ultimate state, a dilute gas of elementary particles expanding exponentially through de Sitter spacetime at a temperature just above absolute zero. This heat-death scenario represents the logical endpoint of the second law of thermodynamics applied to cosmology, but it raises profound questions about the nature of information and entropy in de Sitter space. If information that falls into black holes is eventually returned to the universe through Hawking radiation, what happens to the vast amounts of information encoded in cosmic structure during the long journey toward thermal equilibrium? Some theoretical proposals suggest that quantum mechanical effects might prevent the universe from reaching true thermal equilibrium, maintaining tiny fluctuations that could occasionally generate new pockets of complexity. These quantum fluctuations could, over unimaginably long timescales, spontaneously create new structures ranging from simple particles to complex organisms to entire civilizations. The probability of such spontaneous organization is vanishingly small for any reasonable timescale. But in an eternally expanding de Sitter universe, even the most improbable events will eventually occur. This leads to paradoxical conclusions about the nature of existence and identity in an infinite cosmos, where every possible configuration of matter will be realized infinitely many times across space and time. These speculative scenarios push far beyond current scientific understanding into realms where physics and philosophy converge. They highlight the extraordinary implications of living in a universe dominated by dark energy, where the familiar processes of cosmic evolution represent brief interludes in an otherwise eternal story of exponential expansion. When quantum mechanics meets the curved space-time of de Sitter space, the resulting physics defies every intuition we have developed about the nature of empty space and thermal equilibrium. The marriage of quantum field theory with exponentially expanding geometry creates phenomena so strange that they challenge our most fundamental concepts about vacuum states, particle creation, and the relationship between geometry and thermodynamics. The story begins with a thought experiment that pushes the boundaries of both quantum mechanics and general relativity. Imagine an observer floating freely in de Sitter space, surrounded by the exponentially expanding cosmic geometry, but isolated from any material influences. According to classical physics, this observer should detect nothing at all. The space around them is completely empty, devoid of matter, radiation, or any other form of conventional energy. But quantum mechanics tells a different story. The rapid expansion of de Sitter spacetime continuously stretches quantum vacuum fluctuations, transforming virtual particle pairs into real particles that carry energy and momentum. From the perspective of our isolated observer, the apparently empty vacuum begins to glow with thermal radiation, as if space itself had acquired a finite temperature purely through its geometric properties. This phenomenon represents one of the most profound connections between gravity and quantum mechanics discovered in modern physics. The temperature that emerges from de Sitter quantum field theory is not arbitrary, but follows a precise mathematical relationship involving fundamental constants and the curvature of space-time. The de Sitter temperature equals the expansion rate divided by twice pi times the speed of light, creating a direct link between cosmic dynamics and thermal physics. The mathematical machinery needed to understand this thermal behavior involves quantum field theory in curved spacetime, a synthesis of special relativity, quantum mechanics, and general relativity that pushes the boundaries of theoretical physics. Unlike quantum field theory in flat Minkowski space, where the vacuum state is unique and well-defined, quantum fields in de Sitter space exhibit a rich variety of possible vacuum states with different physical properties. The choice of vacuum state becomes crucial for understanding what different observers detect in de Sitter space. An observer who remains at a fixed spatial location experiences constant acceleration due to the exponential expansion, similar to an observer hovering at constant altitude above a black hole. This acceleration breaks the symmetry of the vacuum state and leads to the detection of thermal radiation with the characteristic de Sitter temperature. The mechanism behind this thermal detection involves the quantum mechanical mixing of positive and negative frequency modes that occurs in accelerated reference frames. In flat spacetime, the distinction between particle creation and particle annihilation operators is preserved by the symmetries of Minkowski space. But in de Sitter space, the exponential expansion scrambles these modes, creating correlations between particle creation and annihilation that manifest as thermal radiation. This thermal behavior extends beyond simple particle detection to encompass the full thermodynamic properties of de Sitter space. The expanding cosmos possesses a well-defined entropy that can be calculated using the standard formulas of statistical mechanics. Remarkably, this entropy turns out to be proportional to the area of the cosmic horizon rather than the volume of space contained within it. Echoing the holographic properties discovered in black hole thermodynamics, the area law for de Sitter entropy suggests deep connections between cosmology and information theory that remain incompletely understood. If entropy measures the amount of information needed to specify a physical state, then the area scaling implies that all the information contained within de Sitter space can somehow be encoded on its two-dimensional boundary. This holographic principle challenges traditional notions of locality and suggests that space-time itself might be an emergent phenomenon arising from more fundamental degrees of freedom. The quantum fluctuations in de Sitter space also exhibit correlations that extend across vast cosmic distances, creating entanglement between widely separated regions of space-time. These quantum correlations survive the exponential expansion and remain detectable even when the correlated regions disappear beyond each other's cosmic horizons. The universe develops a hidden quantum structure that connects causally disconnected regions through non-local quantum mechanical relationships. Understanding these long-range quantum correlations requires sophisticated mathematical techniques borrowed from quantum information theory and condensed matter physics. The de Sitter vacuum state can be constructed using methods analogous to those developed for studying quantum phase transitions in many body systems. The resulting state exhibits features reminiscent of topological order, where global quantum properties emerge from local interactions in ways that cannot be reduced to classical geometry. The stability of quantum fields in de Sitter space presents another set of fascinating puzzles that connect cosmology to fundamental questions in quantum field theory. Unlike quantum fields in flat space-time, which remain stable indefinitely in their vacuum states, quantum fields in de Sitter space exhibit various forms of infrared instability that can lead to dramatic modifications of the cosmic evolution. These instabilities arise because the exponential expansion of de Sitter space continuously generates long wavelength modes that accumulate over cosmic time. For certain types of quantum fields, particularly massless scalar fields with specific interaction strengths, these infrared effects can grow large enough to modify the background geometry itself. The quantum fluctuations cease to be small perturbations and instead become dynamical drivers of cosmic evolution. The mathematical analysis of these infrared effects requires sophisticated resonation techniques that account for the accumulation of quantum corrections over exponentially long periods of cosmic time. The calculations reveal a rich variety of possible behaviors, ranging from stable evolution, where quantum effects remain small, to runaway instabilities that completely destroy the de Sitter solution. One particularly striking example involves the quantum fluctuations of the gravitational field itself during inflation. These gravitational quantum fluctuations generate primordial gravitational waves that propagate through the expanding space-time, carrying information about the quantum nature of gravity during the earliest moments of cosmic history. The amplitude and spectral properties of these gravitational waves encode details about the energy scale of inflation and the coupling between gravity and matter during the quantum gravity era. The detection of primordial gravitational waves would provide the first direct observational evidence for quantum gravity effects in cosmology. These waves originate from quantum fluctuations in the metric tensor itself, representing ripples in the fabric of space-time that were stretched to macroscopic scales by cosmic inflation. Their observation would confirm that gravity exhibits quantum mechanical behavior and would open new windows into physics at energy scales far beyond those accessible in terrestrial experiments. The quantum field theory of de Sitter space also reveals unexpected connections to particle physics beyond the standard model. The thermal radiation detected by accelerated observers in de Sitter space can include particles with masses much larger than the de Sitter temperature, seemingly violating the classical expectation that thermal radiation should be dominated by light particles. This mass threshold violation occurs through quantum tunneling processes that become enhanced in the exponentially expanding geometry. These particle creation processes provide natural laboratories for studying grand unified theories, supersymmetry, extra dimensions, and other extensions of the standard model in cosmic environments. The quantum field dynamics in de Sitter space can amplify subtle signatures of new physics that would be undetectable in flat space-time, making inflation and cosmic acceleration powerful probes of fundamental particle interactions. The mathematical framework for analyzing these effects combines techniques from quantum field theory, differential geometry, and stochastic processes in ways that continue to challenge theorists. The calculations often involve infinite dimensional path integrals over field configurations that span exponentially expanding spacetimes. Advanced techniques from algebraic topology, functional analysis, and mathematical physics are needed to extract finite, physically meaningful results from these formal expressions. Recent developments in holographic duality have provided new perspectives on quantum field theory in de Sitter space by relating it to conformal field theories defined on the cosmic boundary. These holographic descriptions offer complementary approaches to calculating correlation functions, understanding entanglement structures, and analyzing the stability of the de Sitter vacuum. The holographic dictionary translates geometric questions about curved spacetime into algebraic questions about boundary field theories. The experimental verification of quantum field effects in de Sitter space remains an active frontier in observational cosmology. The cosmic microwave background provides a detailed snapshot of quantum fluctuations that were generated during inflation and subsequently evolved through the thermal history of the universe. Future observations will map these fluctuation patterns with unprecedented precision, searching for subtle signatures of quantum gravity, extra dimensions, and other exotic physics. Advanced gravitational wave detectors offer another avenue for probing quantum field effects in de Sitter spacetime. The background of primordial gravitational waves carries information about quantum fluctuations during inflation that cannot be erased by subsequent cosmic evolution. These waves represent fossil evidence of quantum gravity in action, preserved in the geometric structure of spacetime itself. The philosophical implications of quantum field theory in de Sitter space extend far beyond technical physics to touch on fundamental questions about the nature of reality, observation, and cosmic meaning. If the vacuum state of quantum fields depends on the choice of observer and reference frame, what does this say about the objective reality of particle creation and thermal radiation? Are these phenomena genuine features of the physical world, or merely artifacts of how we choose to describe quantum states in curved spacetime? These questions connect to broader debates about the interpretation of quantum mechanics and the role of measurement in determining physical reality. In de Sitter space, the boundary between observer and environment becomes blurred as the cosmic horizon limits what any observer can access, and the thermal radiation emerges from quantum correlations that extend beyond the observable universe. The physics challenges us to develop new conceptual frameworks for understanding quantum mechanics in cosmological contexts where traditional notions of isolated systems and external observers break down. The mathematical formalism required to handle these interpretational challenges involves sophisticated extensions of standard quantum field theory. The construction of the de Sitter vacuum state requires techniques from algebraic quantum field theory, where states are defined through their correlation functions rather than through explicit wave functions. This approach allows for the treatment of quantum fields in curved spacetime without relying on a preferred choice of coordinates or reference frame. The resulting mathematical structure exhibits remarkable richness, with multiple inequivalent vacuum states corresponding to different choices of observers and measurement procedures. The Bunch-Davies vacuum, the alpha vacua, and the Euclidean vacuum each encode different physical assumptions about the initial conditions and boundary behavior of quantum fields in de Sitter space. The choice between these vacua cannot be made on purely mathematical grounds, but requires additional physical input about the cosmological context. This vacuum ambiguity connects to fundamental questions about the arrow of time in quantum cosmology. Unlike quantum field theory in flat spacetime, where the vacuum state is determined by the requirement of Poincare invariance, de Sitter space admits multiple time orientations that are related by the symmetries of the background geometry. The choice of vacuum state effectively selects a preferred direction of time evolution, breaking the time reversal symmetry of the underlying space-time. The breaking of time reversal symmetry has profound implications for the thermodynamic properties of de Sitter space. The thermal radiation detected by accelerated observers emerges from correlations between quantum fields at different times, creating a preferred direction for information flow and entropy increase. This quantum mechanical arrow of time reinforces the classical thermodynamic arrow associated with cosmic expansion. Advanced calculations in de Sitter quantum field theory reveal intricate connections between the thermal properties of space-time and the mathematical structure of quantum correlation functions. The thermal spectrum emerges from the analytic continuation of Euclidean correlation functions, where imaginary time evolution generates the statistical weights associated with thermal equilibrium. This Euclidean approach provides powerful computational tools for calculating quantum effects in curved spacetime. The Euclidean path integral formulation of de Sitter quantum field theory involves integrating over field configurations on four-dimensional spheres rather than hyperbolic spacetimes. This mathematical transformation converts the difficult problem of quantum field theory in Lorentzian de Sitter space into the more tractable problem of statistical mechanics on spherical geometries. The resulting calculations often exhibit unexpected connections to exactly solvable models in condensed matter physics. These mathematical techniques have revealed universal features of quantum field theory in de Sitter space that transcend the details of specific field theory models. The thermal radiation, the correlations across cosmic horizons, and the infrared divergences all exhibit scaling behaviors that depend only on the curvature of space-time and the fundamental constants of nature. This universality suggests deep connections between quantum gravity and statistical mechanics that extend far beyond the de Sitter case. The study of quantum field theory in de Sitter space has also illuminated connections to black hole physics that were not apparent from classical considerations alone. The cosmic horizons in de Sitter space share many properties with black hole event horizons, including the ability to generate thermal radiation and hide information from external observers. This parallel has motivated the development of a de Sitter version of black hole thermodynamics. The thermodynamic laws for de Sitter space involve relationships between the cosmic horizon area, the de Sitter temperature, and the cosmological constant that mirror the familiar laws of black hole mechanics. The first law relates changes in the horizon area to changes in the energy content of space-time, while the second law requires that the horizon area never decreases during any physical process. These laws provide consistency checks for quantum field theory calculations in curved spacetime. The generalized second law for de Sitter space leads to constraints on the types of matter and radiation that can exist in exponentially expanding spacetime. If ordinary matter is added to pure de Sitter space, the entropy contained within the cosmic horizon must not exceed the maximum entropy that can be encoded on the horizon itself. This holographic bound limits the amount of information that can be stored within any finite region of de Sitter space. Violations of the holographic bound would signal the breakdown of semi-classical gravity and the onset of quantum gravity effects that cannot be captured by ordinary quantum field theory in curved spacetime. The approach to this bound during cosmic evolution provides a natural measure of when new physics beyond general relativity becomes important for cosmological dynamics. The holographic principle in de Sitter space has motivated the development of dual descriptions, where the physics of the exponentially expanding interior is encoded in a quantum field theory living on the cosmic boundary. These holographic dualities extend the ADS-CFT correspondence to cosmological contexts, providing new tools for understanding quantum gravity in realistic spacetimes. The boundary theory for de Sitter space typically involves conformal field theories with time-dependent couplings that encode the evolution of the bulk spacetime. The calculation of bulk correlation functions reduces to the computation of boundary correlation functions in the dual theory, often leading to dramatic simplifications in complex quantum field theory problems. These holographic methods have provided new insights into the infrared divergences that plague quantum field theory in de Sitter space. The boundary description often regulates these divergences automatically, revealing finite physical quantities that remain hidden in the bulk formulation. The holographic perspective suggests that the apparent pathologies of de Sitter quantum field theory might be artifacts of incomplete understanding rather than fundamental inconsistencies. Recent developments in holographic duality have also revealed connections between de Sitter space and quantum error correction, where information encoded in quantum systems is protected against noise and decoherence through redundant storage across multiple degrees of freedom. The quantum error correcting properties of de Sitter space might explain how information can be preserved during exponential expansion, despite the apparent loss of causal connectivity. The experimental verification of these quantum field theory predictions represents one of the most challenging frontiers in observational cosmology. The quantum fluctuations generated during primordial inflation have left their imprints on the cosmic microwave background, providing a fossil record of quantum field theory in action during the earliest moments of cosmic history. Future observations will probe these signatures with unprecedented precision. The statistical properties of cosmic microwave background fluctuations encode detailed information about the quantum state of matter fields during inflation. Departures from Gaussianity could signal interactions between different field species or non-linear evolution during the inflationary epoch. The detection of primordial gravitational waves would provide direct evidence for quantum fluctuations of the gravitational field itself. Space-based gravitational wave detectors will extend these searches to much lower frequencies, potentially accessing the stochastic background of gravitational waves generated during cosmic inflation. This primordial gravitational wave background carries information about quantum field theory in de Sitter space that cannot be erased by subsequent cosmic evolution, providing a direct window into quantum gravity during the inflationary epoch. The theoretical framework for predicting these observational signatures continues to evolve as our understanding of quantum field theory in curved spacetime deepens. Multi-field inflation models, models with higher derivative interactions, and models involving extra dimensions all make distinctive predictions for the observable consequences of quantum field dynamics in de Sitter space. The interpretation of current and future observations requires increasingly sophisticated theoretical modeling that pushes the boundaries of quantum field theory, general relativity, and statistical analysis. The interplay between theory and observation in this field exemplifies the iterative process by which scientific understanding advances, with each new measurement constraining theoretical possibilities, while new theoretical insights guide the design of future experiments. The broader implications of quantum field theory in de Sitter space extend far beyond cosmology to fundamental questions about the nature of space-time, causality, and quantum mechanics itself. The thermal properties of apparently empty space challenge traditional notions about the relationship between matter and geometry, suggesting that space-time possesses intrinsic thermodynamic properties that emerge from its quantum mechanical structure. These insights point toward a future synthesis of quantum mechanics and general relativity that goes far beyond the current framework of quantum field theory in curved space-time. The ultimate theory of quantum gravity will likely incorporate the lessons learned from studying de Sitter space, while extending to regimes where the semi-classical approximation breaks down completely. The mathematical tools developed for de Sitter quantum field theory continue to find applications in diverse areas of theoretical physics, from condensed matter systems with analogous symmetries to string theory compactifications that reproduce de Sitter-like behavior. This cross-fertilization between different areas of physics exemplifies the unity of mathematical description that underlies apparently disparate physical phenomena. Despite its mathematical elegance and observational successes, de Sitter space faces a growing array of theoretical challenges that question whether it can serve as a complete description of cosmic evolution. These challenges emerge from the deepest levels of theoretical physics, where attempts to unify quantum mechanics with gravity reveal fundamental tensions that may prohibit the existence of stable de Sitter solutions in a complete theory of quantum gravity. The most serious challenge comes from string theory, humanity's most ambitious attempt to construct a unified theory of all fundamental forces. String theory seeks to describe all particles and interactions as different vibrational modes of tiny one-dimensional objects called strings, operating in spacetimes with extra dimensions beyond the familiar 3 dimensions of space and 1 dimension of time. This framework has achieved remarkable mathematical successes, unifying quantum mechanics with gravity in ways that seemed impossible using conventional field theory approaches. But when string theorists attempt to construct realistic cosmological models within their framework, they encounter a persistent and troubling obstacle. Despite decades of intensive research, no one has succeeded in building a stable de Sitter vacuum within string theory that satisfies all the consistency requirements of the framework. Every attempt to create long-lived exponential expansion within string theory either leads to mathematical inconsistencies or predicts that the de Sitter solution will decay rapidly into some other configuration. This failure has crystallized into what theorists call the swampland conjecture, a set of proposed constraints that distinguish between effective field theories that can be consistently embedded within string theory and those that cannot. According to these conjectures, theories with positive cosmological constants inhabit the swampland of mathematical possibilities that appear consistent at low energies, but become pathological when embedded within a complete quantum gravity framework. The swampland conjectures suggest that any effective field theory admitting stable de Sitter solutions must violate the fundamental principles that govern string theory vacua. If these conjectures are correct, then de Sitter space represents an impossible configuration that appears mathematically consistent only because we lack a complete understanding of quantum gravity. The exponential expansion that seems so natural from the perspective of general relativity may be forbidden by the deeper principles that govern spacetime at the Planck scale. The technical arguments underlying the swampland program involve sophisticated mathematical machinery, borrowed from algebraic geometry, complex analysis, and advanced differential geometry. String theory compactifications typically involve Calabi-Yau manifolds, complex geometric objects whose intricate topology determines the low-energy physics that emerges in 4-dimensional spacetime. The constraints on cosmological constants arise from the geometric properties of these internal spaces and their interaction with quantum corrections that become important at high-energy scales. One particular swampland conjecture, known as the de Sitter swampland conjecture, specifically targets cosmological models with positive vacuum energy. It proposes that the potential energy functions that drive cosmic inflation must satisfy certain slope conditions that make stable de Sitter minima impossible to achieve. Any scalar field responsible for driving exponential expansion must be continuously rolling toward lower energy states, preventing the formation of the metastable vacua required for sustained inflation. If this conjecture is correct, it would have profound implications for both primordial inflation and the current era of cosmic acceleration. Primordial inflation would have to be driven by rapidly evolving scalar fields rather than slowly rolling ones, potentially altering the predictions for observable signatures in the cosmic microwave background. The current acceleration of cosmic expansion would have to be a transient phenomenon, with dark energy evolving toward eventual dilution or decay. These constraints have motivated the development of alternative cosmological frameworks that avoid stable de Sitter solutions while preserving the successful predictions of inflationary cosmology. One promising approach involves quintessence models, where dark energy is represented by a slowly evolving scalar field rather than a true cosmological constant. These models can reproduce the observed cosmic acceleration while satisfying the dynamical requirements imposed by string theory constraints. Quintessence fields exhibit equation of state parameters that can vary with time, allowing for more complex evolutionary scenarios than pure de Sitter expansion permits. During the current cosmic epoch, quintessence can mimic the effects of a cosmological constant closely enough to match current observations. But unlike a true cosmological constant, quintessence is predicted to evolve, potentially leading to future changes in the cosmic expansion rate that could be detected by next-generation astronomical surveys. The observational distinction between quintessence and a cosmological constant requires precision measurements of how dark energy properties change over cosmic time. This has motivated increasingly sophisticated observational programs designed to trace the expansion history of the universe with unprecedented accuracy. Future space missions will map the three-dimensional positions of billions of galaxies, measure gravitational lensing effects with exquisite precision, and search for temporal variations in fundamental constants that could signal evolving dark energy. Another class of alternatives to de Sitter cosmology involves modifications to Einstein's theory of general relativity itself. These modified gravity theories propose that the gravitational field equations receive corrections at large distance scales that could account for cosmic acceleration without requiring dark energy. The modifications typically involve additional gravitational degrees of freedom that become important when curvature scales approach the size of the observable universe. FR gravity represents one of the simplest modifications, where the Einstein-Hilbert action is generalized to include arbitrary functions of the scalar curvature. These theories can produce cosmic acceleration through purely gravitational effects, eliminating the need for mysterious dark energy components. The additional gravitational degrees of freedom modify the propagation of gravitational waves and the growth of cosmic structure in ways that could potentially be detected by future observations. More exotic modifications involve extra-dimensional scenarios where our four-dimensional space-time is embedded within a higher-dimensional bulk space. The cosmic acceleration could arise from the leakage of gravitational effects into these extra dimensions, creating apparent repulsion in our observable universe. These models connect dark energy to fundamental questions about the dimensionality of space and the ultimate structure of reality at the smaller scales. Emergent gravity theories represent an even more radical departure from conventional approaches, proposing that space-time itself is not fundamental, but emerges from more basic quantum mechanical degrees of freedom. In these frameworks, cosmic acceleration could arise from collective quantum effects that become important when the universe reaches sufficiently large scales. The apparent dark energy would represent a manifestation of quantum entanglement operating across cosmic distances. The experimental verification of these alternative frameworks presents enormous challenges for observational cosmology. Many modified gravity theories make predictions that differ from general relativity only at scales comparable to the size of the observable universe, making direct tests extremely difficult. The effects often involve subtle modifications to the growth of cosmic structure or the propagation of gravitational waves that require unprecedented observational precision to detect. Quantum gravity effects add another layer of complexity to the theoretical landscape surrounding de Sitter space. Loop quantum gravity, causal dynamical triangulation, and other approaches to quantum gravity each impose their own constraints on possible spacetime geometries. Some of these approaches suggest that the smooth exponential expansion of de Sitter space might be replaced by discrete quantum mechanical jumping between different geometric configurations. The role of quantum fluctuations in determining the ultimate fate of de Sitter space remains an active area of research with important implications for cosmic evolution. Even if classical de Sitter solutions exist, quantum mechanical effects might destabilize them over sufficiently long time periods. The quantum decay of false vacuum states represents a fundamental process in quantum field theory that could eventually terminate any period of exponential expansion. These decay processes involve quantum tunneling events, where the scalar fields responsible for cosmic acceleration spontaneously jump to lower energy configurations. The probability for such transitions is typically exponentially suppressed, making them extremely rare events. But over the vast timescales relevant to cosmic evolution, even exponentially rare processes can become important for determining the ultimate fate of the universe. The calculation of vacuum decay rates in de Sitter space involves sophisticated techniques from quantum field theory that push the boundaries of current mathematical understanding. The exponential expansion of the background spacetime modifies the standard instanton calculations used to compute tunneling probabilities in flat space. The resulting formulas involve complex geometric objects and advanced mathematical techniques from algebraic topology and differential geometry. If vacuum decay processes are sufficiently rapid, they could prevent the formation of stable de Sitter vacua, even in theories where such solutions appear mathematically consistent. This would provide another mechanism by which quantum gravity effects could eliminate de Sitter space from the landscape of allowed cosmological solutions. The universe would be condemned to eternal evolution, never reaching the thermal equilibrium associated with exponential expansion. The philosophical implications of these theoretical challenges extend beyond technical physics to fundamental questions about the nature of scientific knowledge and cosmic understanding. If string theory truly prohibits stable de Sitter solutions, what does this say about the relationship between mathematical consistency and physical reality? Are we forced to abandon de Sitter cosmology despite its observational successes, or do the theoretical constraints point toward deeper principles that we have yet to understand? These questions highlight the tension between bottom-up approaches that begin with observational evidence and top-down approaches that start from theoretical principles. De Sitter space emerged from Einstein's field equations and found support through astronomical observations of cosmic acceleration. But string theory approaches the problem from the opposite direction, asking what cosmological solutions are consistent with a complete theory of quantum gravity. The resolution of this tension may require conceptual breakthroughs that transcend current theoretical frameworks. Perhaps the swampland conjectures point toward new physics that operates at energy scales intermediate between current experiments and the Planck scale. Or perhaps the apparent conflicts between string theory and de Sitter cosmology will dissolve when we achieve a more complete understanding of quantum gravity in cosmological contexts. The debate over de Sitter space thus represents more than a technical disagreement within theoretical physics. It embodies fundamental questions about how we construct scientific knowledge, how we balance theoretical elegance against observational evidence, and how we navigate the uncertain terrain at the frontiers of human understanding. The ultimate resolution will likely reshape our picture of cosmic evolution and our place within the vast tapestry of space-time. As we reach the end of our journey through the mathematics and physics of de Sitter space, we find ourselves confronting questions that stretch far beyond technical cosmology to touch the deepest mysteries of existence itself. The exponentially expanding spacetime that Willem de Sitter discovered in his Leiden study has revealed itself to be not merely an abstract mathematical construction, but potentially the key to understanding both the ultimate origins and the final destiny of everything that exists. The story we have traced spans more than a century of human intellectual achievement, from Einstein's revolutionary insights about the nature of gravity to the cutting-edge observations that reveal our universe's accelerating expansion. At every stage, de Sitter space has served as both a theoretical laboratory for testing our understanding of space-time and a concrete prediction about the behavior of the cosmos on its largest scales. Perhaps most remarkably, this single mathematical solution to Einstein's field equations appears to describe not one, but potentially three distinct epochs in cosmic history. If the inflationary paradigm is correct, our universe began its existence in a de Sitter-like state, expanding exponentially during the first fraction of a second after the Big Bang. The quantum fluctuations generated during this primordial inflation created the seeds of cosmic structure that eventually grew into the galaxies, stars, and planets we observe today. The current era of cosmic evolution may represent a return to de Sitter dominance as dark energy gradually overwhelms matter and radiation to drive accelerating expansion into the far future. This cosmic acceleration connects our present moment to both the earliest instance of cosmic history and the ultimate fate of everything that exists. We live in a universe bookended by de Sitter space, with the complex drama of cosmic evolution unfolding in the narrow window between primordial and future exponential expansion. But the significance of de Sitter space extends far beyond its role as a cosmological solution. The mathematical framework developed to understand exponential expansion has revolutionized our approach to fundamental questions about the nature of space-time, quantum mechanics, and thermodynamics. The discovery that empty space can possess temperature, entropy, and thermodynamic properties purely through its geometric structure has opened entirely new research directions at the intersection of gravity and quantum theory. The holographic properties of de Sitter space suggest that our traditional concepts of locality and dimensionality may be fundamentally inadequate for describing the deepest levels of physical reality. If all the information contained within a three-dimensional volume can be encoded on its two-dimensional boundary, then perhaps space itself is an emergent phenomenon arising from more fundamental degrees of freedom that operate according to principles we have yet to discover. These insights connect de Sitter cosmology to some of the most ambitious projects in contemporary theoretical physics. String theory, loop quantum gravity, and other approaches to quantum gravity all grapple with questions that were first illuminated by studying the properties of exponentially expanding spacetime. The thermal radiation that emerges from de Sitter horizons provides crucial clues about how quantum mechanics and gravity might be unified within a single theoretical framework. The observational program to test the predictions of de Sitter cosmology has driven some of the most sophisticated experimental efforts in the history of science. From precision measurements of the cosmic microwave background to gravitational wave astronomy to next-generation galaxy surveys, astronomers are pushing the boundaries of observational precision to test theoretical predictions about exponential expansion and its consequences. These observations have already confirmed many of the key predictions of inflationary cosmology, and revealed the accelerating expansion that suggests our universe's de sitter future. But they have also raised new puzzles that challenge our theoretical understanding. The precise flatness of cosmic geometry, the unexpected acceleration of expansion, and the apparent fine-tuning of cosmological parameters all point toward physics beyond our current theoretical frameworks. The challenges facing de sitter cosmology from string theory and quantum gravity add another layer of complexity to this intellectual landscape. The swampland conjectures suggest that stable exponential expansion might be incompatible with a complete theory of quantum gravity, forcing us to consider alternative frameworks that could preserve the observational successes of de sitter cosmology while satisfying deeper theoretical constraints. These theoretical tensions highlight the provisional nature of our current understanding and the likelihood that major conceptual revolutions lie ahead. The resolution of conflicts between observational evidence and theoretical principles may require new mathematical tools, novel physical concepts, or fundamental changes in how we think about the relationship between space-time and quantum mechanics. The philosophical implications of de sitter cosmology challenge traditional notions of cosmic purpose and meaning. If exponential expansion represents both our origin and our destiny, then the complex structures we observe around us, including life and consciousness themselves, emerge as transient phenomena in cosmic history. The vast majority of space and time consists of empty, exponentially expanding de sitter spacetime, with brief interludes of complexity occurring only under very special conditions. This perspective might seem to diminish the significance of human existence and terrestrial concerns. We appear to inhabit a rare oasis of complexity in a cosmic desert of exponential expansion. The stars that illuminate our night sky, the planets that harbor life, and the galaxies that structure the cosmic web all represent temporary departures from the de sitter equilibrium that characterizes most of space-time. Yet, this apparent cosmic insignificance can be reframed as a source of profound meaning rather than nihilistic despair. The emergence of complexity, consciousness, and understanding in a universe dominated by exponential expansion represents an extraordinary violation of cosmic entropy, a temporary victory of organization over chaos that defies the thermodynamic tendencies that govern most of cosmic evolution. The fact that matter has organized itself into structures capable of contemplating their own origins and destinies suggests that even in a de sitter-dominated cosmos, the universe possesses an inherent tendency towards self-awareness. Through the emergence of intelligence, the cosmos develops the capacity to understand itself, to decode the mathematical principles that govern its evolution, and to appreciate the elegant geometric structures that determine its fate. This self-reflective capacity of the universe represents perhaps the most remarkable feature of cosmic evolution. In a cosmos that began as a quantum fluctuation in primordial de sitter space and will end as empty, exponentially expanding space-time, brief episodes of complexity have emerged that are capable of comprehending the entire cosmic story. The universe has become conscious of itself through the evolution of intelligence within its temporary oases of complexity. The mathematical tools that allow us to understand de sitter space represent the culmination of thousands of years of human intellectual development, from the geometric insights of ancient Greek mathematicians to the differential geometry of 19th century mathematics, to the quantum field theory of the modern era. Each generation has contributed essential pieces to the conceptual framework needed to decode the cosmos. This cumulative character of scientific understanding highlights the collaborative nature of the human quest to comprehend the universe. No single individual could have discovered the principles of de sitter cosmology in isolation. The insights required contributions from Einstein and de sitter, from Hubble and Hawking, from Guth and thousands of other researchers whose work collectively illuminated the exponential expansion that shapes cosmic evolution. The technological achievements that enable precision cosmological observations represent equally impressive triumphs of human ingenuity and cooperation. The space telescopes that map the cosmic microwave background, the gravitational wave detectors that sense ripples in space-time itself, and the supercomputers that simulate cosmic evolution all embody humanity's determination to push beyond the limitations of direct sensory experience to comprehend cosmic truths. These technological and intellectual achievements suggest that consciousness represents more than a mere accident of cosmic evolution. The capacity to understand mathematical principles, to decode observational data, and to construct theoretical frameworks that reveal hidden cosmic truths points toward deep connections between mind and cosmos that we are only beginning to appreciate. The continuing development of artificial intelligence and machine learning may represent the next phase in this cosmic awakening. As we develop computational systems capable of processing vast amounts of observational data and exploring complex theoretical landscapes, we extend the universe's capacity for self-understanding beyond the biological limitations that have historically constrained scientific progress. Future developments in quantum computing may provide the computational power needed to simulate quantum field theory in curved spacetime with the precision required to test the deepest predictions of de Sitter cosmology. These simulations could reveal new connections between quantum mechanics and gravity that remain hidden from analytical approaches, potentially pointing toward the unified theory of quantum gravity that has eluded physicists for decades. The search for extraterrestrial intelligence represents another frontier where de Sitter cosmology intersects with profound questions about cosmic meaning. If consciousness has emerged elsewhere in the universe, then the temporary oases of complexity scattered throughout cosmic history may be connected by networks of communication and understanding that transcend the limitations of individual civilizations. The cosmic horizon structure of de Sitter space suggests that such communication networks face fundamental physical limits, imposed by the geometry of exponentially expanding spacetime. Civilizations separated by sufficient distances will eventually lose all possibility of communication as cosmic acceleration carries them beyond each other's observable horizons. The universe fragments into causally isolated regions, each containing whatever intelligence happens to emerge within its boundaries. This fragmentation raises profound questions about the ultimate fate of knowledge and understanding in an exponentially expanding cosmos. Can intelligence find ways to preserve and transmit information across cosmic horizons? Are there physical processes that could allow consciousness to persist through the heat-death scenario predicted by de Sitter thermodynamics? These questions push beyond current physics into speculative territory, where science fiction and theoretical cosmology begin to converge. The answers may depend on discoveries about the fundamental nature of information, consciousness, and physical law that lie far beyond our current understanding. Perhaps consciousness represents a fundamental feature of the universe that cannot be reduced to the behavior of ordinary matter and energy. Or perhaps intelligence will discover ways to manipulate space-time geometry itself, transcending the apparent limitations imposed by exponential expansion. As we contemplate these ultimate questions, we return to the remarkable fact that a mathematical solution discovered in a quiet observatory in Leiden has illuminated cosmic truths that span the entire history of the universe. Willem de Sitter's exploration of empty, exponentially expanding spacetime has revealed connections between geometry and physics, between quantum mechanics and gravity, between the smallest and largest scales of physical reality. The de Sitter solution demonstrates the extraordinary power of mathematical reasoning to reveal hidden aspects of cosmic truth. By following the logical implications of Einstein's field equations into seemingly abstract territory, de Sitter uncovered a space-time geometry that would prove central to understanding both cosmic origins and cosmic destiny. The universe speaks to us in the language of mathematics, and those who learn to decipher this language gain access to cosmic secrets that remain hidden from purely empirical approaches. In the geometry of de Sitter space, the universe whispers both its birth cry and its final silence. The exponential expansion that may have created the cosmos in a quantum fluctuation billions of years ago continues to operate today, slowly but inexorably transforming the rich tapestry of cosmic structure back toward the empty, thermal equilibrium of pure de Sitter space-time. We live in the narrow window between these exponential eternities, temporary witnesses to the brief flowering of complexity in an otherwise simple cosmos. Yet perhaps this apparent simplicity conceals deeper truths that we have yet to discover. The mathematical elegance of de Sitter space, the profound connections it reveals between seemingly disparate areas of physics, and the central role it plays in cosmic evolution, all suggest that exponential expansion represents more than a mere mathematical accident. In the curved space-time that de Sitter discovered, we may be glimpsing fundamental principles of cosmic organization that connect the deepest levels of physical law to the grandest scales of cosmic structure. The story of de Sitter space thus becomes a metaphor for the human quest to understand our place in the cosmos. Through patience, creativity, and collaborative effort, we have decoded geometric relationships that govern the birth, evolution, and ultimate fate of everything that exists. In doing so, we have participated in the universe's ongoing project of self-discovery, adding our own chapter to the cosmic story that began with quantum fluctuations in primordial space-time and may end with the thermal equilibrium of eternal expansion.